Welcome. After learning about some fundamentals about the membrane gas separation in the natural gas systems, now we shall be looking into some of the applications of these fundamentals to solve the real life problems in the membrane gas separation. Let us first take the first problem. In this problem, we have to separate two components A and B, and we are given the ideal separation factor alpha BA as 4.5. The permeability of the component A is given as 3 barer, and we have been asked to determine the permeability of component B. So, here we have that we first write what data are given to us, and then we write what we need to find out. Then we go to the definition of the ideal separation factor, in this case alpha BA star, and this is the ratio of the permeabilities, and then we find that PB is equal to PA tilde into alpha BA star, and then from this we find the permeability of component B as 13.5 barer. So, this is a very simple problem in which we find that how to determine the permeability of a component from the permeability of another component and the value of the ideal separation factor. Next we come to this problem. In this problem we have been given that carbon dioxide is to be separated from a mixture of 10% carbon dioxide and 90% methane using a membrane at 35 degree centigrade and 10 atmosphere total pressure. In this we are using a asymmetric polysulfone membrane with 1 micron skin layer thickness, and the permeate side is continuously swept with nitrogen gas, so that there is no accumulation of the permeate gas on the permeate side, because if there is accumulation of the permeate gas, what will happen, that it will reduce the driving force by increasing its partial pressure. So, the nitrogen is used so that the partial pressure of the particular component, in this case carbon dioxide, can be kept minimum. So, that is how we are sweeping the permeate side with nitrogen gas, and we are asked to determine the carbon dioxide flux through the membrane, the average diffusivity of carbon dioxide in polysulfone, and the permeance of methane in the polysulfone, and these are the data given to us, and we have been asked that we can neglect the permeation of the nitrogen through the membrane, because if nitrogen also permeates the membrane, it will change the driving force, it will change the resistance to the mass transfer. So, in this case we are neglecting the permeation of the nitrogen through the membrane. So, we have to use this particular data, ideal separation factor carbon dioxide to CH4 is 22, then Henry's law constant is given here, and this is the permeability of carbon dioxide. Now, for solution, what we first do, we list out all the data given to us, the value of the ideal separation factor, then this SA, then PA, and this thickness of the membrane, and we have to find out these values, the flux, diffusivity, and the permeance. First, for the flux, we write this equation. In this equation, we need to know the partial pressures. So, on the retented side, the partial pressure is given by the product of the mole fraction and the total pressure, and that is coming to 1 atmosphere. And as we learnt earlier, that when the composition is given in terms of some fraction, if there is nothing mentioned for gas, we assume it to be mole fraction or the volume fraction. So, that is why we are taking this 0.1 as the mole fraction, and on the permeate side, because of the nitrogen sweep, we are assuming that there is no accumulation of the gas on the permeate side. So, the partial pressure is almost kept to 0. So, with these values, what we do, we plug in the values in this expression for the flux, and after plugging in, we find this is the value of the flux. Please mind it that use the appropriate units. So, when you are starting to solve these problems initially, always write the units so that you do not commit any mistake in getting the final result. So after that we find this is the value of the flux. Next we come to this value of the permeance, which is nothing but the SA into dA, and this we are taking the values of SA and dA, and we find that this is the value we get, and the permeance value has been given to us 5.6 barad, and from this the diffusivity is found to be 2.02 into 10 to the minus 8 centimeter square per second. So this is the diffusivity value of the component CO2 through the membrane. Next we come to the ideal separation factor, which is given as the ratio of the permeabilities or permeance. This is given as 22, and so from here we find the value of this for component B, the permeability comes to about 0.254 barad. And once we get this value, we get the permeance like this, that we put this value of Pb tilde and divide it by the thickness of the membrane, and this is the result for the permeance we get for the component B. So we can see that how this particular problem can be solved to find out the flux, the diffusivity and the permeance of the various solutes. Next we come to a problem which is very common in the membrane, and in this case we have taken a problem which tries to analyze that what would be the effect of any kind of defect, like in terms of the pinhole on the membrane. So here we have the problem. We are again considering some asymmetric polysulfone gas separation membrane with a skin thickness of about 0.15 micron, and there is a pinhole. Now what happens with the pinhole? To cover the pinhole, again some other kind of polymer is used, and one of them is polydimethylsiloxane, and this is in short called PDMS. So this particular polymer is coated on the skin to cover up the pinhole, and this particular coating will also have its own thickness, that is about 0.3 micron. Now because this thickness is more than the thickness of the particular membrane, so this particular coating will also offer its resistance to the mass flux. But we have to do it to save the membrane, so that we do not have to go for a new membrane. So for some initially we may use such kind of coating to cover up any kind of pinhole. The coating also fills the pinhole, and what we find that the cross section of the pinhole occupies about this 5 into 10 to the power minus 6 of the membrane surface. That is, this zeta represents the ratio of the cross section area of the pinhole to the cross section area of the actual membrane surface. Now we have oxygen enriched air to be prepared, and what we are doing, that we have oxygen nitrogen mixture. Oxygen is represented by A and nitrogen by B, and we have all these value of the permeabilities given here, and we are also given this for the coating we are given. So this represents the permeabilities through the membrane, this M represents membrane, and these are the permeabilities through the coating, C represents the coating, and all in the barad. There is a spelling mistake here, this is in barad. So we have to determine the overall permeability and the ideal separation factor of oxygen in the composite membrane. So here we are representing the pictorially how it looks like, that here we have this membrane, and on this we have the skin, and the skin is represented by these black things. So there, and these hollow things, the white ones are the pinholes, and to prevent the pinholes, what we are doing, we are using this PDMS layer. So what we find, that whenever the permeation is occurring, one permeation is occurring through this and one is occurring through this. Now in this case, if we just magnify this thing, we find there are different the resistances are coming into picture. One resistance is due to the resistance through the particular PDMS coating, and one resistance is coming through the membrane and this particular pinhole. Now as we learned that this PDMS coating is also filling up the pinhole. So whenever the solute is passing, this particular region, this is a pinhole region, and the membrane region, through this the flux is occurring in parallel, whereas through these two parallel resistances are in series with the resistance through the particular coating. So, if we draw an electrical analogy to this, we find that there is this coating resistance which is the RC, and then we have the parallel resistances, one through the membrane and one through the coating which is in the membrane side. So, that is this RCM represents the resistance offered by the coating material on the membrane side, and this particular resistance and the membrane resistance, they are in parallel, and these two resistances are in series with the resistance through the coating. So, that is how we draw this diagram on electrical analogy. Now, what we do that we put all these values which are given to us, and we find that the 1 by zeta is 1. That means zeta represents the fraction of the coating and 1 by zeta represents the fraction of the membrane. We find the value is so small that we can assume that almost even in the presence of the pinhole, almost every surface of the membrane is occupied by the membrane. And we have to find out these permeability values and the ideal separation factor. Now, in this case what we do, we go by the calculation of the resistances. So, as per our figure, we find these are the resistances through the coating and the membrane together, and these are resistance through the coating. So, this resistance is in series with these two resistances, these are parallel resistances, and we just do the mathematical rearrangement to get this particular equation. After getting this equation, we put the various values given in the problem to get the resistance here, and then we find the resistance through the for the another component B. This is component A and this component B, that is oxygen and nitrogen, and here we have the values of these permeances from these resistance values, and this is the value of for oxygen, this for the nitrogen. So, that is how we find the permeabilities of these two components from the given data. And what we find here, that this oxygen is passing at a much higher rate than nitrogen by looking at this data. Next, we come to find the ideal separation factor, and we find that by taking the ratios of the permeabilities or the inverse of ratios of the resistances, we find that this is the value of the ideal separation factor. This shows that this particular membrane is selectively separating oxygen by letting oxygen to pass through it, while by retaining the nitrogen over it. So, that is how we are able to take care of the pinhole in our analysis of the membrane separation. Further details may be found from these two references. Thank you.